So first of all, we're going to start off by looking at some examples of our functional groups to look at how these work in basically some examples of what molecules are and how you would actually go about drawing these and their different structural types. So we've got two main structure types which you'll be required to be able to recognize and one which you'll be required to be able to actually draw yourself. So we've got on the left, we've got the structural formula, and then we've got the skeletal formula. So the structural formula is showing each individual atom and how it is bonded to every other atom, whereas the skeletal formula shows this but without any letters to specifically denote what these are. And so with the skeletal structure, we're saying that we're assuming that any hydrogens are just there, they're not explicitly ever shown in this, and then we're assuming that the carbons is the end of any of the molecule, so the two ends of these for ethane being the two carbons, and then the hydrogen just being assumed to be there. With longer molecules, they'll be forming a zigzag shape, and so any ends of the molecule and any points of the molecule will be assumed to be carbons. And so with these, you only need to know how to draw the structural formula, but you also need to be able to recognize the structural formula and draw the structural formula. With the skeletal formula, you only need to be able to recognize that one. You don't need to be able to draw it. Our next example which we can look at is 2-methylbutane. So 2-methylbutane is a molecule which we've got here, where we've got 4 carbons along the carbon backbone, and then along on the second carbon in, we've got what's known as a methyl group, so that being a group of methane, basically, but it's a separate branch off the original molecule. And so we can see this structure on the left here. The way this is being laid out is a little bit different from the one which we saw with ethane, where we've specifically got these sticks and letters to specifically show the exact layout of the molecule. With this one here, we've got a slightly condensed structural formula, so you will commonly see these ones as well. And so basically what these are is we've got a carbon, and we're just saying that these 3 hydrogens are bonded off this carbon here. So not necessarily that it's anything different from the other one too much, it's just condense it down so that you can draw them in a smaller space. And so for example, the next carbon along, it's saying that it has been bonded to one other hydrogen, and so that hydrogen would be drawn in the other formula as being sticking out the bottom here. And same with this carbon here, this is methyl group here is drawn as coming off of this second carbon, and these hydrogens would be surrounding this particular carbon molecule, but it just hasn't been drawn like that, just so it can be condensed down. Then on the right, we've got the skeletal formula. So the skeletal formula of this, showing that we've got one carbon here, the next carbon here, another carbon here, and another carbon here, so that being 1, 2, 3, 4 carbons. Then we can see we've got this chain sticking off, so that end of that line being another carbon there, so that being this particular methyl group here. And so what we can notice about the difference between this and this is that this is actually just a flip of the other molecule. So instead of counting 1, 2, 3 and saying that it's a 3-methylbutane molecule, 3-methylbutane doesn't exist because we always want to preference the lowest number on the methyl chain. So we'd actually be naming it from right to left instead, and we want to preference the lowest number for the methyl group. So we'd name it as 1, 2, and so that methyl group's on the second carbon, it will be a 2-methylbutane molecule. So the next one we're going to look at looks very, very complex when you first look at it, but when you break down the naming of this one, it's actually a lot simpler than it first appears to be. And so what we can see here is that we've got a molecule which is named as 7-ethyl 2,2-dimethyl 4-propylnonane. And so when you're faced with a long and big molecule name like this, or a big molecule, or if you were shown just this structure here and it's a big molecule like this, the first thing you always want to look at is what is at the end of the molecule. What is the suffix for this particular molecule name? And so we can see that the suffix is nonane, so that being a 9-chain long alkane molecule. And so we can see if we count along this chain down the bottom here, we want to find the longest possible continuous chain. So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that's 9 carbons long along the longest possible chain. We could also count it 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4, 5, 6, 7, 8, 9. Or if we counted from here, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's plenty of ways, but the longest possible chain which can be formed is 9 carbons long, so we're going to be saying it's a nonane molecule. Next, we can look at what all these different functional groups are, which we have. So it's saying on 7, we have an ethyl group. So on the 7th carbon along the molecule, we have an ethyl group. So we can count along and we can go 1, 2, 3, 4, 5, 6, 7. We can see on the 7th carbon along, we've got 2 carbons branching off of that. And so those 2 carbons branching off are what we know as an ethyl group, because it's like an ethane branch. But when it's a branch, we change it to ethyl. And so that's the 7-ethyl. Next, we can see we've got a 2,2-dimethyl group. So it's saying that on the 2nd carbon, we've got 2 methyl groups. So 1, 2, we've got a methyl group on this side and a methyl group on this side. And so it's important to note that this is not considered an ethyl group, because although they're on the same carbon, they're on opposite sides. So one carbon, one of these methyl groups is on this side, one of these methyl groups was on this side. If they were both on the same side, so if we went carbon and then bonded another carbon here, that would not be known as a methyl group. That would then be known as an ethyl group, and so instead it would just be a 2-ethyl. But because they're on opposite sides, they're 2 separate groups. That's a methyl group there, and that's a methyl group there, and so hence it's 2,2-dimethyl. The next one is saying 4-propyl. So it's saying we've got a 3-carbon chain long branch on the 4th carbon along the chain. So we can go 1, 2, 3, 4. And we can see we've got 1, 2, 3 carbons branching off the 4th carbon along the main chain. And so this here would be our propyl group, because it's like a propane chain, being 3 carbons long, except it's a chain, so and it's branching off, so it's a propyl group. So hence we end up with 7-ethyl, 2,2-dimethyl, and 4-propyl, and then nonane being the entire length of the main chain. So it's really important when you're faced with these complex ones like this that you focus on breaking down the naming, because they do appear very complex at the beginning, but once you break down the naming system and into its constituent parts, it makes a lot more sense and it makes it a lot easier to figure out what it is. The final one we're going to look at is 3-ethyl 2-methylheptane. So we'll do the same thing to break this one down. So we'll look at what the end of the molecule says. So we've got heptane. So that meaning that the longest possible chain along the backbone of this molecule is going to be 7 carbons long. So we can count 1, 2, 3, 4, 5, 6, 7. So that's 7 carbons long at the longest point along the chain. We could also double check here, 1, 2, 3, 4, 5, 6, 7. That part there could also be the longest part of the chain. We could count 1, 2, 3, 4, 5, 6, 7. That there could be our longest chain. Either way, our longest possible chain is always going to be 7 carbons long. So hence it's going to be heptane at the end of the molecule. The next thing we want to look at is what our functional groups are. So we've got an ethyl group and a methyl group. So when we look for our ethyl group, we can see that's on the third carbon along. So we want to count 1, 2, 3. We can see that's the third carbon along. We've got 2 carbons bonded off this, a 2-carbon chain. And so on the third 1, 2, 3 carbon along of the chain, we've got an ethyl group. And so that creates this 3-ethyl at the start. Then going along, we've got a 2-methyl group. So we've got a methyl group, a single carbon branch on the second carbon along the chain. So we can go 1, 2, and this here we can see we've got a methyl group located here, as we've got 1 carbon branching off the main chain. And so that's what our extended structural formula would look like for this particular molecule. The next thing we want to look at is what would our skeletal formula look like for this particular molecule. So we can see this one here is actually a flip of this molecule here, much like the other time. So we can be counting from left to right, from right to left as opposed to left to right, because if we look for the ethyl group, we can see the carbons being on the points and on the ends of the molecules. So we'd have 1 carbon, 2 carbons, 3 carbons, and we can see we've got a branch located here. So 1 carbon, 2 carbons. So that 2-carbon long branch there would be our ethyl group. So 1, 2, 3, our ethyl group's on the third carbon along the chain. And then our methyl group is going to be on the second carbon along the chain. So going 1, 2, we've got 2-methyl there. And so that methyl group being the end of that stick there. So that just shows how we can name these molecules based on their skeletal formula or their structural formula, and how they can be shown to be counted from left to right or right to left, depending on whichever way they've been drawn. They're the exact same molecule, just drawn in different ways.